Hello, I'm Patty Simpson with Simpson Math. Let's talk about hypothesis testing. So a hypothesis test is a technique for testing a claim about a population parameter using statistical principles. So if you think about when I asked you or when I told you I knew when your birthday was, and I knew with 95% certainty that your birthday was between 1970 and 2010. I was sure of that, 95% certain. But if I started going and asking my students, is that your birthday? And I started hearing over and over again, no, I was born before 1970. I might adjust my thinking. I might think to myself, my confidence interval, something about those birthdays is different than what I thought it was. So that's kind of the idea of a hypothesis test, is that we have some statistic or some parameter that we think is true about our population. And then some evidence starts coming up that makes us think that maybe that parameter is not true anymore. And we'd like to test to see if that statistic or that parameter has changed. So here's another example of that. So back to the ages. So maybe I think my college students have gotten older. I'm noticing their birthdays are before 1970. And we thought before that the average statistic or the average age of our students was 22. Just making up a number there. But let's say that we thought our students' average age was 22. And now I'm thinking, well, maybe our average age is older. Well, let's think about this 22 for a minute. If I go out and I choose a sample of students and I look at that sample of students and I find the average age of that sample of students, remember that that average age, that sample mean, is part of a sampling distribution of sample means. And that sampling distribution of sample means, as long as I took a big enough sample, random sample, should be part of a normal distribution. So here I have this normal distribution. That's not very pretty, but let's go with it. And, then we did our confidence intervals. I knew that I was 99.7% confident that that age of a student, if I went out and got another sample and another sample, that 99.7% of the time, my sample mean would fall somewhere in this range. Okay, but I now think that my students are older than 22. Something's changed. Maybe the workforce is not as open to older people, and so they're coming back to school to get a college degree or something. So I think that my population has changed. And so I think my age of my students is older. So I have an alternative hypothesis. An alternative hypothesis we write with a capital H and a lowercase a as a subscript. Our alternative hypothesis is just a mathematical statement about our parameter. And it's the hypothesis that we want to gather information or evidence in favor of. It's also called the research hypothesis. So my research hypothesis, my alternative hypothesis, is that the age, and this is what we mean by a mathematical statement, the age is greater than, I think they've gotten older, our age is greater than 22. So I've made an alternative hypothesis. I think the age is greater than 22. So my alternative hypothesis is the age is greater than 22. Then the null hypothesis, or we denote that with a capital H and a lower script 0 there, is the mathematical opposite of the alternative hypothesis. And it's always going to include the equality, always. So here, if the age, I thought it was the age is greater than 22, then the mathematical opposite of that would be less than 22. But it always includes the equality. So it's less than or equal to 22. And this is our null hypothesis. Now, what we're going to do is we're going to go out and gather evidence. And we're going to try to find enough evidence to convince us that maybe the age has gotten older than 22, Or we're going to look for evidence, and we're going to see maybe that evidence convinces us or shows us that the age is not greater than 22. So if when we go out and collect the sample now, and we find that sample mean, we know that 95% of the time my sample mean should fall within 2 standard deviations. Well, if I get some sample mean out of there that's greater than that, that's out here somewhere, now I'm going to think that's weird. It's kind of like getting a student whose birthday is before 1970. I go, that's a little bit weird. Well, if I get a sample mean that is way out here, I go, that would be really, really rare that would happen. In fact, if this is 95% of the time, that means on the ends it's 5% of the time, and only 2.5% of the time would I get something that far out there. So then I start to think, maybe our mean isn't 22. Maybe our mean is something different. But if when I'm gathering evidence, if I get a mean that is within that 95%, then I go, well, no, I guess I'm wrong. That our age really is within that 22. It is something that it makes sense for it to be there. Even if I get something out here, well, 95% of the time I'm going to get a mean within 2 standard deviations of the actual mean. So once we have found this alternative hypothesis and this null hypothesis, our next step is going to be to gather evidence to help us to see, is our hypothesis true or not? And the way we're going to gather evidence is we're going to see, do we get some value way out there where we go, that's weird that I'm getting that value way out there. So that's just the basics of a hypothesis test, is that we have some idea about our parameter that's different than what we think the actual parameter is. And then we're going to gather evidence to test that theory to see, is it maybe the same, or do we find some evidence that makes us think that our parameter has changed? Let's talk about hypothesis testing. The first step in performing a hypothesis test is to identify the alternative and null hypothesis. So let's do that now. Let's identify the alternative and null hypothesis for a few scenarios. First of all, a hypothesis test is just a technique for testing a claim about the population parameter using statistical principles. And the alternative hypothesis, we denote with a capital H and a subscript A, is a mathematical statement about the parameter, and it's the hypothesis that the researcher is aiming to gather evidence in favor of. It's also called the research hypothesis. And then the null hypothesis is the mathematical opposite of that alternative hypothesis. It's always going to include the equality and the equal sign in there. And this null hypothesis is always assumed to be true. So you can kind of think of it as if you were in a courtroom and you had a defendant, you just assume that that defendant is not guilty. That's your automatic assumption. Until proven otherwise, he's not guilty. And the same thing is true with the hypothesis test, that the null hypothesis is assumed to be true unless you can gather enough evidence to show that that alternative hypothesis could be true. So this is kind of like that person in the courtroom. You're going to assume that they're not guilty. Here we're going to assume our null hypothesis is true. And then if you happen to gather enough evidence to show that you see guilt without reasonable doubt, well, that's the same thing with our alternative hypothesis. We're going to gather enough evidence to show that alternative hypothesis might be true. So that's kind of the idea of the hypothesis testing. And the first job is just to find the alternative and null hypothesis. So let's do that for a couple of scenarios. Here we have a manager of a candy manufacturing plant claims that since his machinery was overhauled, the mean weight of the chocolate produced is smaller than the correct mean weight of 4 ounces. So he thinks that his chocolate is not producing enough. The machines are not producing enough chocolate. So his alternative hypothesis is that that mean weight is less than 4 ounces. That's his alternative hypothesis. So this just denotes that alternative hypothesis. He thinks the mean is less than 4 ounces. Well, if his alternative hypothesis is that the mean is less than 4 ounces, then your null hypothesis just takes that and it's the mathematical opposite. So instead of being less than, it's going to be greater than 4. And the null hypothesis always includes the equality. So it's greater than or equal to 4. So here's our null hypothesis there. So our alternative is that it's less than 4, and the null is that it's greater than or equal to 4. So remember that when we go out and we collect a sample, random sample of at least 30 chocolate bars, and we weigh them, and then we find that mean of those chocolate bars, that mean is part of a sampling distribution that is approximately normal. And the mean of that sampling distribution would be the same as the population. So we would expect it, if the population mean is 4, then we would expect our mean of the sampling distribution to also be 4. Then we created those confidence intervals where if we go out 68% confident, we'd be going out 1 standard deviation. If we're 95% confidence level, then we'd be going out 2 standard deviations. And if we're 99.7% confidence level, then we'd be going out 3 standard deviations. So, with that confidence interval, if I then go out and grab a sample of the chocolate bars and I weigh them, I would expect that weight, that mean, if the population parameter, if the mean weight is 4, I would expect that mean weight of my sample to be within 3 standard deviations of this mean. If, however, I get some value way out here, then I can start to think to myself, that's really curious, that's weird. So that's kind of the idea of this hypothesis testing, that we're going to assume that our null hypothesis is true, that we're going to get some value in here. And if we get some value in there, then we're going to go, well, it looks like, we don't have enough evidence to show that the machine is doing something different. But if when we get our mean, our value is way down here, it's out, 2-3 standard deviations out, then we're going to go, hey, I've collected some evidence to show that it actually is less than what it should be. So, if I get some value, depending on my confidence level, if I get some value out here, then that would let me know that's some evidence showing that it's a little bit less. Let's do another example where we find that alternative and null hypothesis. So here at Northwest Mississippi Community College, syllabi for an online class states that students should expect to spend 10 hours a week doing coursework for each 3-hour credit class. The director of e-learning for the college is concerned students are being required to spend more than 10 hours per week doing work. So here the e-learner thinks that the mean is supposed to be 10 hours per week, but the e-learner director thinks that it is more than 10 hours. So that mean, that average amount of time that they're spending, the director thinks is greater than 10 hours. That is our alternative hypothesis. Then the null is just the mathematical opposite of that. So here this was greater than, so therefore the null would be less than the 10. And the null always includes our equality. So that is the null hypothesis, is that it is less than or equal to 10. So again, we are going to assume that this is true, that the average amount of time that they're spending is less than or equal to 10, unless we gather enough evidence to show that, hey, that might not be the mean after all. And the way we're going to do that is we again know if we go out and collect a sample, random sample of at least 30 people, we know that that sample mean is part of this sampling distribution. And that sampling distribution should be approximately normal. And the mean of that sampling distribution should be the same as the population mean, our parameter. So it's part of this normal distribution, something like this. And then, one standard deviation out if we have a confidence level of 68%. 68% of the time when we go out and collect a sample mean, it would fall within one standard deviation. 95% of the time when we go out and collect a sample mean, it would fall within 2 standard deviations of the mean. So depending on our confidence level, tells you how many standard deviations we go out. Then we're going to say, well, I've gone out, I've collected my mean, and I get this mean that is here. Well, I kind of expect that. 95% of the time, I expect to get a sample mean within 2 standard deviations. But if I get a sample mean way out here, then I go, there's something weird about that. Something weird's going on. That's not it can happen. It could happen, but that's evidence against that 10 hours per week. Let's try one more example. So after learning that Peter Collet of Switzerland could hold his breath for 19 minutes and 21 seconds underwater, a group of students decided to conduct their science fair project around the amount of time an average adult can hold his or her breath. Part of the group found research to suggest that adults can hold their breath for 30 seconds when submerged in lukewarm water. So there's this understanding that adults, our parameter mean is that adults can hold their breath for 30 seconds underwater. The other half found evidence to suggest that the mean time is different if the water temperature is cooler. The group would like to test this claim about adults holding their breath in cold water. Now, notice in this one that they didn't tell us if they think they can hold it longer or if they can hold it shorter in cold water. It just says that the mean is different than that 30 seconds if it's in cold water. So to show that mathematically for our hypothesis, our alternative hypothesis, we're going to say the mean is just not equal to that 30 seconds. That's their hypothesis, their alternative hypothesis. Then the null hypothesis is the mathematical opposite of that. And it always includes the equality. So in this case, if my alternative hypothesis is it's not equal to, then the null hypothesis is that my mean is actually equal to that 30 seconds. So again, what are we going to do? We're going to go get a group of adults, put them in some cold water, have them hold their breath and time them. Then we're going to find the average, the sample mean of that group. That sample mean, if I've collected a group of random sample of more than 30, should be part of a normal distribution, that sampling distribution. So, and I would expect my mean to be about 30. So here's that normal sampling distribution. And just as before, if I go out, 68% of the time, I expect my sample mean to fall within 1 standard deviation. So it could be out here a little bit, it could be out there a little bit, that's normal. We expect that 68% of the time. Even 95% of the time, we expect it to come out 2 standard deviations. So if I get a sample mean that's somewhere out here, it doesn't show me evidence that that 30 is not true. So I wouldn't go around rejecting my null hypothesis just because I get something a little bit out here. I kind of expect that within a 95% confidence level. And then 3 standard deviations out, is 99.7%. But if I get something way out here, well, then all of a sudden I start thinking maybe that mean is incorrect. Or if I get something way down here, then then I start thinking, something's a little bit weird. Maybe the mean is not 30 seconds, because that would happen so rarely. It could happen, but it would be evidence against that 30 seconds. So that's kind of what we mean, that beginning part, our piece of doing a hypothesis test. The first thing we have to do is just determine what is our alternative hypothesis, and then from that, what is our null hypothesis. Let's talk about some vocabulary surrounding hypothesis testing. First of all, a hypothesis test is just a technique for testing a claim about a population parameter using statistical principles. So we're going to look at some parameter, some value from the population, and we're going to test that using some different statistical principles. Then an alternative hypothesis, denoted with a capital H and a subscript A, is a mathematical statement about the parameter and its hypothesis that the researcher is trying to gather evidence in favor of. It's also called the research hypothesis. So this is the hypothesis that the researcher has that they are testing. Then the null hypothesis, or this is a capital H with a subscript 0 there, is the mathematical opposite of the alternative hypothesis. It will always include the equality. And we practiced finding some alternative and null hypothesis earlier. Then a test statistic is the value used to make a decision about the null hypothesis, and the statistics derived from the sample. So let me explain a minute. So we have some parameter out there that we think is true, but the researcher decides, hey, I have some hypothesis that maybe that statistic is too high, or that parameter is too high or too low, or it's just not equal to that. Then what we're going to do is we're going to test that parameter. And in order to do that, we're going to go out and collect a sample that's at least 30, and it's a nice random, simple random sample, so that we know that that test statistic, that statistic from that sample, fits into that sampling distribution that has that normal shape to it. And then that is the test statistic. The statistic we get from our sample, we're going to use that statistic to test our hypothesis. And so therefore it's called the test statistic. Then that test statistic is said to be statistically significant if it is far enough away from the presumed value of the population parameter to conclude that it would be unlikely for the sample statistic to occur by chance if the null hypothesis were true. Remember that we're going to assume that the null hypothesis is true. It's just like in a court of law, you assume that the person there is not guilty until you see enough evidence to convince you otherwise. It's the same thing with our null hypothesis. We're going to assume it's true until we get a test statistic that's so far away from our parameter that we're like, there's something weird there, that it is statistically significant. Let me draw you a picture and kind of show you what's happening here. So when we collect a statistic, a mean or a proportion from a sample, and it's part of that sampling distribution, we know then that that sampling distribution has that normal shape to it. So our mean is there in the middle, and we expect our sampling distribution to have the same mean as the population. So we created confidence intervals to say, well, when we collect that sample, the mean may not be right there. It might be a little bit to the left or to the right of that, but we know that because it's in a normal distribution, 68% of the time it's going to fall within one standard deviation. 95% of the time it's within 2 standard deviations, and 99.7% of the time it's within 3 standard deviations. So we expect it to maybe be a little bit bigger or a little bit smaller, but we expect it to be within 3 standard deviations for sure from the mean. If it's further out than that, then we go, there's something really weird happening. And we can adjust our confidence level. So maybe I'm only looking at the 68%. Well, then if it's further out than that, then I say, well, that is statistically significant for me. That's enough evidence for me to see that mean is, for me to reject the null. We'll talk about that a little bit later. 95% is usually what we use. So if it's at least, out there to that 95%, if it's further out on either end, then I start going, maybe that's big enough for me to say it's statistically significant. It's far enough out there that it would be unlikely for me to get that statistic. Or, out 3 standard deviations, maybe I'm using that as my confidence level. Which, by the way, the level of significance, which we use this alpha to denote that, is the probability of making an error of rejecting a true null. Remember that when we talked about our confidence intervals, that our confidence level we denoted as C? Well, with our level of significance, we're going to use alpha, and it's just 1 minus C, or you can think of it as the complement of C. So if my confidence level is 95% or 0.95, then my level of significance would be 0.05. It would be 1 minus that 95. And that is your level of significance. So that statistical significance depends upon your level of significance. How far out is it? If my level of significance is 0.3 or 0.15, I would need to be way out there. But if my level of significance is like 0.1 and 10%, then it would be closer to the mean. So my level of significance tells me how far out that is for it to be far enough away for the probability for that probability to be, ooh, that's weird, there's something weird going on. So the level of significance we'll look at when we're doing a hypothesis test, and that'll help us determine whether or not it's statistically significant. Let's look now to see what are the conclusions that we can come to from a hypothesis test. Let's talk about the conclusions that we make when dealing with hypothesis tests. There are 2 different conclusions we can come to. The first is to reject the null hypothesis if the test statistic calculated is found to be statistically significant. In other words, it is far enough away from the population parameter for us to consider it statistically significant. Then we reject the null in favor of the alternative hypothesis. Our second thing that can happen is that we can fail to reject the null hypothesis if our test statistic is not statistically significant. So let me explain a little bit. First of all, always picture a court room where a defendant comes in, and we are presuming that that defendant is not guilty unless we get enough evidence to be able to say that the defendant is guilty. We have to collect enough evidence. The same thing is true with our hypothesis here. Our null hypothesis, we're going to presume that it is true unless we get enough evidence that we can go, we reject it. But we have to collect enough evidence. Then in the courtroom with the defendant, we never say that the defendant is innocent. If we don't get enough evidence to say that he's guilty, then we say he's not guilty. We never say, though, for sure that he's innocent. It just means we didn't collect enough evidence to show that he's guilty. So we say he's not guilty. The same thing's true with our failing to reject the null. When we have a null that we don't get enough evidence for, we don't say that that null hypothesis is true. Instead, what we do is we say, well, we don't have enough evidence to reject it. So we're going to fail to reject it. Let me give you a small picture to deal with. We know that when we go out and collect a sample and we find a mean from that sample or a proportion from that sample, that's part of a sampling distribution. So if we have our sampling distribution and we take the mean of that sampling distribution, we expect our test statistic, well, we know our test statistic falls into that sampling distribution. And we know that if it's in a normal curve, that within 1 standard deviation from the mean, it's going to fall there 68% of the time. If it's within 2 standard deviations from the mean, it's going to fall there 95% of the time. And then within 3 standard deviations is 99.7% of the time. So we decide how far out is far enough for it to be statistically significant. But let's say I go out and I collect that test statistic. I collect that test statistic and it falls way out here. Well, then I say, hey, that is statistically significant. And if it is way out there and we say it's statistically significant, then we reject the null. We say, hey, we reject you. And it gives us evidence in favor of whatever our alternative hypothesis was. But if when I collect my test statistic, it falls, somewhere in here where I expect it to be, well then that's not enough evidence for me to be able to reject the null. So in this case, I'm going to fail to reject the null. It's not far enough out for me to reject the null. I failed to reject the null. And so I did not gather enough evidence for my alternative hypothesis. So here I fail to reject, whereas this one, we would reject the null. So those are our 2 different outcomes. Now we can make mistakes, and we'll look at that in a little bit. There are different errors we can make because it is possible to get something that far out there even when the mean is here. So we might reject the null even though we shouldn't. Just like sometimes we put a defendant in jail when actually they're not guilty. And then we could fail to reject when it turns out that mean is wrong. Just like sometimes we don't put a defendant in jail. We say they're not guilty when they really are guilty. So we can make those same errors here as well. We'll look at that though later. So the 2 conclusions we can come to are to reject the null and to fail to reject the null. Let's look at an example here. At Northwest Community College, syllabi for online classes state that students should expect to spend 10 hours a week doing coursework for each 3-hour course credit. The director of e-learning for the college is concerned students are being required to spend more than 10 hours per week doing work for each class. We looked at this earlier and we saw that our alternative hypothesis, that the e-director said that the mean was going to be more than 10. So that meant that our null hypothesis was that it was less than or equal to 10. Then a hypothesis test with a 5% level of significance is performed on the director's claim. Remember that 5% level of significance is the complement to our confidence level. So if it's a 5% level of significance, that tells me that it's a 95% confidence level that I'm dealing with. The result is to reject the null hypothesis. Does this conclusion support the director's claim? Well, we're going to reject the null. So let's look and see what's happening here. So my mean is here at 10. And if I reject the null, if I reject the null, that means that I got it statistically significant. It was far enough out here that I'm going to reject that null. And sure enough, if I reject this null, it means that there is enough evidence to show that the director's claim may be correct. In which case, maybe we need to switch those syllabi to say, hey, it's going to be more than 10 hours, Or the e-learner director needs to go to the teachers and say, hey, it turns out it's taking longer than what you expected. Maybe we need to narrow this down a little bit. So that when we reject the null, it does support our alternative hypothesis. Let's look at another example. Here's another example. Based on historical data, the Board of Education for one large school district believes that the percentage of high school sophomores considering dropping out of school is at least 10%. A high school counselor believes that the percentage is too high. A hypothesis test with a level of significance of 2% is performed on the counselor's claim. The result is to fail to reject the null hypothesis. Do the findings support the counselor's claims? First of all, this level of significance of 2% tells me that I need to have a test statistic that is out far enough that it is at the 2% probability that I get it. Or we could say that we have a 98% confidence level. So here the result is to reject the null. Remember that again, when we collect our sample, our mean would be here in the middle. In this case, it would be 10%, or in this case, a proportion. Our proportion would be in there in the middle, 10%. And our alternative hypothesis here, the counselor is claiming that that proportion is less than 10%. And then the null is that it is greater than or equal to that 10%. So we're going to take and we're looking for something small enough down here to support that counselor's claim. The counselor's looking for enough evidence that it's way down here and it's 2% chance down here that we would get that test statistic. And then we would say it's statistically significant. The result is to fail to reject the null. Notice if I'm failing to reject the null, that means it's closer in here. So their test statistic was not statistically significant. So that did not support the counselor's claim. Instead, we say that we fail to reject this. It doesn't mean that that's true. It just means we did not get enough evidence to say that we reject it. So it does not support the counselor's claim. So those are the conclusions that we can make from hypothesis tests. Let's talk about conclusions of hypothesis tests and the errors we can make when we have those conclusions. So the first type, or type 1 error that we can make in our conclusion, is to reject a true null hypothesis. So in this case, we go out and we gather our test statistic and we get a rare outcome where that particular test statistic is way out. And it's some weird reading that turns out to be statistically significant. So the probability we get it is really, really low. And so we reject our our null hypothesis. But it turns out that that null hypothesis is correct. We just got a weird reading for some reason. So that's type 1 error. Then a type 2 error is to fail to reject a false null hypothesis. So another thing that can happen is we go out and we get our test statistic, and that test statistic is not statistically significant. It's not way out there. It's near the mean in that distribution where we think it should be. And so therefore we fail to reject a false null hypothesis. Let's look at an example. Insurance companies commonly use 1,000 miles as the mean number of miles a car is driven each month. One insurance company claims, due to our more mobile society, the mean is more than 1,000 miles per month. The insurance company tests its claim with a hypothesis test and decides to reject the null hypothesis. Assume that in reality, the mean number of miles a car is driven per month is 1,250. Was an error made? If so, what? Well, let's just look at some of the things we've learned about so far. So for instance, we know the alternative hypothesis here is the insurance company is making an alternative hypothesis, a research hypothesis. They're saying that the mean is actually more than 1,000 miles. In which case, that means that our null hypothesis is the mathematical opposite of that, where we take our mean and instead of being greater than, it's going to be less than 1,000. And the null hypothesis always has that equality sign. So then the insurance company goes out and it tests its claim. And remember that 1,000 is here. And we have some normal distribution that statistic is going to be a part of, that sampling distribution. And the insurance company tests the claim and decides to reject the null hypothesis. That means that they had to have gotten some value way out there in what we will learn about as the rejection region. So they get some value that's way far out, that is statistically significant. Assume that in reality, the mean number of miles a car is driven is actually 1,250 miles. So we were assuming that it was this one. We're rejecting the null because it's way out there, so we're rejecting that null and we're saying we think it is more. And it turns out it is more, so there was not an error made. In this case, no error was made. They rejected the null, and sure enough, the mean is larger. So they had support for their claim, and sure enough, it's an actual true claim. So there was no error made in this case. Let's do another example. A study on the effect of television viewing on children reports that children watch a mean of 4 hours of television per night. Kiko believes that the mean number of hours children in her neighborhood watch television per night is not 4 hours. She performs a hypothesis test and rejects the null hypothesis. Assume that in reality, children in her neighborhood do watch a mean of 4 hours of television per night. Did she make an error? If so, what? Okay, let's start by just reviewing some things we know. First, Kiko had an alternative hypothesis. She thought that the mean number of hours that children in her neighborhood watch is not 4. Notice she doesn't say it's greater than or less than. She just says it's not 4. So mathematically, I'm going to say the mean is not equal to 4. So that's her alternative hypothesis. Now, for the null hypothesis, it's that opposite mathematical statement, and it always includes the equality. So here it's not equal to, but our null is equal to. Then she goes out and performs a hypothesis test. Again, we know that that sample mean that she's going to collect, assuming she gets a simple random sample of at least 30 kids in her neighborhood, and it's random sample, then she could have the mean of that sample will be part of a sampling distribution that should be approximately normal with a mean of the same as the population parameter. And she says she rejects the null hypothesis. In other words, she got some value so far out there, either way up here or way down there, that she said, that's so statistically significant that I'm going to reject the null. So she rejected that null hypothesis. Assume that in reality, the children in her neighborhood do watch a mean of 4. So she rejected that null. She said, no, they don't watch 4, but in reality, they do watch 4. So she did make an error. It turns out that she rejected a true null hypothesis. So let's look and see which error did she make? she made a type 1 error. She rejected a true null hypothesis. So there, she actually came up with information, something really rare, or maybe her sample just wasn't good, something where she rejected her true null hypothesis. Let's do one more example. So here's one last example. A television executive believes at least 99% of households in the United States have at least one television. An intern at the executive's company is given the task of using a hypothesis test to determine if the percentage is actually less than 99%. The hypothesis test is completed, and based on the sample collected, the intern decides to fail to reject the null hypothesis. If in reality 96.7% of households own a television set, was an error made? If so, what? Let's first start with our alternative hypothesis. What is it that the intern is looking at? What is that intern's hypothesis? Well, we're talking about proportions since we're in percents. So that proportion is less than 99% is what they're trying to determine. So they say that their proportion is less than 99%. Well, then mathematically, if my alternative is less than 99%, then mathematically the opposite of that would be greater than 99%, and the null always includes your equal sign. Then it says the hypothesis test is completed and based on the sample. So again, proportions are like means in that if we have a sample that's greater than 30 and it's a simple random sample, then we have this normal distribution that we're dealing with. And so let's have this normal distribution. And so then they collect a sample and they decide to fail to reject the null. So if we're not rejecting the null, if we're failing to reject it, that means that when we got our statistic, it's somewhere close enough in there so that we don't reject the null. We go, hey, maybe it's okay. We don't have enough evidence to show that that's not true. So, maybe it's there, or maybe our sample statistic is here. Wherever it is, it's not far enough out. It's not statistically significant. So he says, we're going to fail to reject that. So it does not support this claim that it's less than 99%. Instead, it supports this where it's at least 99%. If in reality, 96.7%, so this is not true. It turns out that it's not true at all. So we should have rejected it since it is less than that 99%. We should have rejected it. We did not reject it. We failed to reject it. So he did make an error. And the error he made was he failed to reject a false null hypothesis. So he made a type 2 error there. He failed to reject that false null hypothesis. So what we've looked at so far is when we are making a hypothesis test, the first thing we have to do is come up with our hypothesis. And then mathematically, the opposite is that null. We go out, we collect some statistic, and then we see if that test statistic is far enough out, if it's statistically significant. And if it is far enough out, then we reject our null. But if it's not far enough out, then we fail to reject the null. But we have to be careful with that because we can make errors. So we have to understand that these two errors can be made. We can reject a true null on occasion, and we can fail to reject a false null. Math Made Simple is Simpson Math. Thanks for watching.